Science Alliance! Hello, my IGCSEers. So this is kind of, it's lesson 8 of electricity, and we're rounding off a little bit. So we've still got, I think we've only got 3 lessons to go. We're going to move on to things like power, how you wire a plug, what earthing means, that kind of thing, watts and joules and things. But this is sort of the last of our circuit diagram lessons. So hopefully it's not quite as brain melting as previous lessons. We're going to play a little bit of bingo. I'm going to do you a quiz. First of all, last week, we need to do a little recap. Do you remember we looked at graphs of different components? So we looked at if you take the voltages and the currents through like a bulb or a resistor or a diode, and you draw them on a graph, what the graph looks like. And I kept showing you this diagram. So last week we looked at voltage current graphs for, are you ready? Are you ready? I just said it, and I had it all on screen. Look, even color coded. Fixed resistors, that's the symbol for a fixed resistor, yeah, the resistance doesn't change, that's a rectangle. We looked at voltage current graphs for bulbs, the circle with a cross through it, and diodes. It's a terrible diagram, the triangle with the line and the arrows. And I kept saying, I'm really sorry, this circuit diagram is bobbins. You couldn't actually use this circuit to get these results. So today we're going to look at why. Why not? Why could you not use this circuit that I've drawn on the screen here to complete this table? You couldn't get different currents and voltages from this circuit and then draw that graph. Why? I tell you what, flipping you around. Using the experience I have now of teaching this lesson on Facebook a couple of times, I'm going to assume that some of you have forgotten what a diode is and give you some heavy clues, and then hopefully you'll be able to get all 3 reasons. So you remember what a diode is? A diode is just something that only lets current through in one direction. So last week we were looking how if you put this current in like the right direction, the forward bias, forward facing direction, and current runs through it in the direction that the arrow is pointing, then everything's fine. It's got a really, really low resistance in the forwards direction. And if it's a light emitting diode, if it happens to have a light on it, the light will light up. But if you turn it around, it's got an incredibly high resistance in the opposite direction. So this current flowing through this way, the bulb would not light up. No current would flow, basically hardly any through the circuit. So one of the things I pointed out to you was that my gorgeous little sort of toy light emitting diode here, my LED, has got a little resistor stuck to the back of it to increase the resistance of the circuit that it's in so that the bulb doesn't melt. Because as I say, LEDs, any kind of diode, light emitting diode or otherwise, have got a really low resistance when current's flowing in like the forwards direction. And if it was too much current, then yeah, the bulb would melt, you'd start to smell things, and it would be all smoky. Okay, that's quite enough clues. Here we go. Why could you not use this circuit that I've drawn on the board here to complete this table of results? Okay, so you've got 2 cells, so it's a battery. You've got the positive end of the battery facing upwards, negative facing downwards. You've got an ammeter in series, you've got a diode there in series, and you've got a voltmeter measuring the voltage across the diode. 3, 2, that's a bit brutal, isn't it, counting to 3? There's 3 reasons. I don't think you're going to be able to spot them all. But I will be silent for like a couple of minutes. Put my little cards up. I said I'd be silent for a couple of minutes. You know that I meant seconds. Okay, so some of you, if my Facebook experience serves me well, are saying things like, the diode's the wrong way around, or the battery's the wrong way around. I like that. But there's what are there? 2 more? Let's have a go. So first of all, the one that no one got on Facebook, so well done if you got this. Let's say this battery is 6 volts, okay? This battery setup here is giving each charge in this circuit 6 joules of energy, yeah? 6 volts means 6 joules of energy per charge. So the charges have got 6 joules of energy. So what's the voltage across this diode? It's going to be the same, isn't it? Because remember, pizzas never go back to the shop if you've been to previous lessons. So we know that the voltage across the diode is 6. Cool. Let's say that the ammeter is reading like 10 amps. So we write that in there. Then what do? You can't get anything else, can you? There's no way of changing the voltage across the diode. There's no way of changing the current in the circuit. So you've just got one dot. That's not a graph. That's not going to work. So there's no way of changing the voltage. The first thing you need is this guy. This is a picture from the 1800s, to be honest. The schools that I worked in, they haven't changed that much. This is called, well, it goes by many names, but the thing we're calling it today is a variable resistor. Essentially a massive coil of wire. So it goes in series in the circuit. You see there's little bits of wire coming off it. You attach it to the circuit by those two pieces of wire. And then this top thing that I've put a star on, that's the slider. So you basically just move the slider so that the current has to flow through just a tiny bit of wire or loads and loads of wire, and that changes the resistance of the circuit, okay? I'll link you to a good website where there's a sort of proper picture of one. But this is the symbol for it. Pay very close attention, because this was catching people out in bingo at the end of the lesson, and I'm not going to show you this many times. It's a resistor, the boring rectangle, but it's got an arrow like stabbing through it to show that it's variable. This resistor can change its resistance. It's a variable resistor, okay? So let's put one of those in the circuit. Here we go. Now, will this circuit allow you to complete this table? No, it won't. Why not? Well, we can change the voltage now. This is, see, you could get quite complicated here, couldn't you? You could have a little think about why changing the resistance of that resistor changes the voltage. Do you know that? You've got an LED, you've got a diode, right? A component in a circuit with 6 volts over it. Why will putting a resistor in that you can change the resistance by sliding it? Why will that change the voltage? You remember that in a series circuit, a complete loop, voltage is shared. So we have talked about voltage as being like the amount of pizzas that a motorbike is delivering, okay? So if it's like 4 volts, it'd be 4 pizzas per motorbike. So if it's one component, that component gets all the pizzas, 4 volts across it. If you put 2 components in, then if they've got exactly the same resistance, they share the voltage equally, so they get 2 pizzas each. But obviously, if you can change the resistance of one, then you change how much voltage is shared across it. It's a bit further than I went on Facebook, but you know, you can't tell me that you're bored or not understanding, so I'm going for it. We could also have used a variable power supply. That's another way of changing the voltage. This is just a pack that you plug in. It's got a knob on it that says 1 volt, 2 volt, 3 volt. So that's nice and easy. Here is the symbol for a power supply. I have written variable power supply to show that it's variable. But you could just stick that in the circuit as well, okay? So we don't have a variable resistor in this one. We've just got a power supply. You change the voltage of that. You obviously change the voltage across the diode. So that would be fine, either of those. Yeah, it's still not working because, as many of you will have pointed out by now, diodes have very little resistance in the right direction. So we need to add a resistor so it doesn't get too much current and melt. So let's add a resistor to the circuit, but it's still not working. Why not? It's because, look, this is the positive side of the battery, and this is the negative side of the battery. And if you remember convention, we said last week how you say, it's not true, but you say that current flows from positive to negative, because when electricity was discovered, they didn't know about electrons. They just assumed that electricity was flowing from positive to negative. So that's how the symbol on the diode has been drawn. That's how the diode's been designed. We're going to have to turn the diode around. Now current is flowing from the positive to the negative through the diode in the right direction. Phew! So you will actually get readings. And we've got this resistor, you understand that? We've got the resistor in there so that the resistance of the circuit isn't so low that you don't get masses of current and melt this thing. Fine. Right. Quiz time! Here is a circuit on the board. Are you going to be able to use this circuit to complete this table? So you need lots of different voltages and currents so that you can plot those in a graph and get the results that we got last week, right? So you've got a battery with the positive facing upwards, you've got an ammeter in series, you've got a bulb in series, you've got a variable resistor in series, and you've got a voltmeter measuring the voltage across the bulb. Is that okay? 3, 2, 1. Yeah, it's fine, isn't it? That's fine. Doesn't matter which way around a bulb goes. You've got a current and a voltage, and you can change the voltage. Yeah, great. Okay, what about B? You've got a variable power supply this time, an ammeter in series, a bulb in series, and you're measuring the voltage across the bulb. Are you going to be able to plot a good graph from that? 3, 2, 1. Yeah, fine, isn't it? Just change the voltage, and that'll change the current, change how much the current is pushed through. Yeah, great. C, you've got variable power supply with positive on the upside and negative on the downside. You've got an ammeter and a resistor in series, and you've got a diode pointing upwards, and you've got a voltmeter measuring the voltage across the diode. Is that okay? 3, 2, 1. No. What's the problem? The diode's the wrong way around, isn't it? Look, at the moment it's backwards, so that would be facing loads of resistance. You wouldn't get any readings. We'll turn the diode round and now it's fine. D, what about that? Variable power supply, positives on the top, negatives on the bottom, ammeter in series, diode facing downwards. You've got a resistor in there as well, and a voltmeter measuring the voltage across the diode. 3, 2, 1. Yeah, that's fine. Resistor protecting the diode, current's travelling in the right direction. Yeah, lovely. What about E? Variable power supply, voltmeter in series with a bulb and an ammeter in parallel across it. What do you think? 3, 2, 1. So this is a classic thing that you should hope that they test you on at IGCSE. You've put your voltmeter and your ammeter in wrong, haven't you? Look at that. That's not going to work at all. Excuse me. Do you remember me saying voltmeters have got, the point of a voltmeter and ammeter is to measure what's happening. They don't want to change anything about the circuit. That spoils the whole point. So a voltmeter has a really high resistance so that when it's measuring like across a bulb, say, in parallel, the current doesn't choose to go through the voltmeter, because that would be bad. You want as little voltage as possible through the voltmeter, because otherwise you're affecting the circuit. And an ammeter has a really low resistance so that it can go in series and not affect the current passing through it. So this is all wrong. F, variable power supply, positive on the top, negative on the bottom, ammeter in series, diode point on the bottom pointing left, resistor, and a voltmeter measuring the voltage across the resistor. 3, 2, 1. That's not ideal, is it? Look, you're measuring the voltage across the wrong component. So your list is going to be the voltage across the fixed resistor and not the voltage across the diode. So no, that's not going to work either. G, how many other? I think there's just 2 more. I think so. You got a battery with a positive end facing upwards and a negative end facing downwards, an ammeter in series, a diode facing downwards, a voltmeter reading the voltage across it, and a resistor, a fixed resistor in there. Are you going to be able to get results from that? 3, 2. It's funny, isn't it? You can use the word quiz and it sounds quite fun, but it's still brain melting. 1. No, what's the problem with that? You've got a fixed resistor protecting the diode. The diode is pointing in the right direction. Look, there's no way of changing the voltage again. You're just going to have 1 dot on your graph. You need a fixed resistor. Note the circuit symbol, a boring old rectangular resistor with an arrow stabbing it. Or you need a variable power supply. And finally, what about this one? It's a battery again. Positive is upwards, negative is downwards. You've got a variable resistor in there. You've got a diode pointing downwards. You've got an ammeter in series and a voltmeter in parallel across diode. Is that okay? 3. I mean, this one probably would be okay. 2, 1. But there is a little something, isn't there? Really, you want to put a resistor in that circuit as well, so that the diode doesn't melt when the currents get too high. Okay. Phew. Now everything is fine. A quick note, because yeah, we're going to play circuit symbol bingo at the end. This is the symbol, we haven't looked at it before, for a power supply. There's just 2 dots. It's like a switch, yeah? But a switch, you've got another line with a dot coming off it that can be open and closed. The power supply is just open. We'll do a bit more about this when we do electricity in the home. But a lot of people were thinking that this was a variable power supply. That's just a power supply. Any kind of power supply. That's why I was writing variable across it, to show that it was variable. But that is just the symbol for a power supply. Is that okay? If you get a bingo too early, don't say that I didn't warn you, all right? Okay, so last week we were looking at if you built that circuit correctly and you did collect a load of different voltages and currents, you could plot them on a graph and you get these different graphs. Oh, pretty lovely. So you can see a fixed resistor, when the current doubles, the voltage doubles, when the voltage triples, the current triples. So it's got a proportional relationship, directly proportional, straight line. And diodes don't do anything in the negative direction. There's no current flowing. And lamps, as they get warm, their resistance increases because there's more collisions. So they do a funny S-shaped thing. We get to learn about 2 more things today. We get to learn about light-dependent resistors. Excuse me. And we get to learn about thermistors. Ooh. So here's a graph of how resistance, I've just written light. I should have written light intensity really. If you get a light-dependent resistor and you shine a light on it, this graph is telling you what happens. You've got resistance on the y-axis and light, should say light intensity, considered flux on the x-axis. But basically, as light increases, look what happens. What happens, please? You tell me. What happens to a light-dependent resistor as light shines on it? As you shine more and more and more light on a light-dependent resistor, what happens? You got a graph? You tell me. The graph starts high and then it swoops down low, but it doesn't quite touch the bottom. I don't think this is rocket science, but I will be silent for like 2 seconds. Its resistance decreases, doesn't it? Yes, look at that. All right, slightly harder question. Why doesn't the line reach to the bottom? Why doesn't the line go all the way to the bottom? So resistance starts high when there's 0 light, and then the resistance gradually decreases and decreases and decreases, but it never quite touches the bottom. Why is that? Literally clamping my hand over my mouth for 5 seconds. It's because that if it touched that line, it would be 0 resistance. And you just don't ever get 0 resistance in real life, right? What is resistance? It's just usually electrons in a wire bumping into the atoms, the positively charged ions in the wire. It's collisions. And you can't get a wire with like no atoms in it. So it's very unlikely that you will ever get anything with 0 resistance. But yeah, resistance does get lower. Okay, so first of all, instead of saying light-dependent resistor, can we just say LDR? Oh, so much easier. So yeah, the circuit symbol for an LDR, a light-dependent resistor, don't get it confused, like a lot of people are doing in bingo, with the variable resistor. The variable resistor, you can change resistance of, it's the slidey thing, the arrow is stabbed through it. A light-dependent resistor just has light shining on it, like that, okay? Here's a picture of what they look like. They're really quite beautiful. Yeah. Here's one that's got 3. Nice, isn't it? So one of the uses of light-dependent resistors is they can be used in like floodlights, maybe at football games, or for like security lights. They are made of semiconducting materials. So let me just tell you what that means. You don't actually need to know this for your IGCSE, but I feel like it's really difficult to remember how an LDR behaves unless you know this. So we've talked about insulating materials, yeah? Like plastics, rubber, current can't flow through them at all. We've talked about conducting materials, like a wire that allows the current to flow through. Semiconducting materials, that's what it says on the tin, is like they conduct a bit. So if something's a semiconductor, it has electrons that are kind of bonded to its atoms. But when those electrons get energy, they kind of like start to move around more, okay? So you get more current flowing. So like, no, I do not want to read my iCloud terms and conditions right now. Thank you, phone. So yeah, a semiconductor like lead sulfide or something, when the atoms get energy. So in a light-dependent resistor, when light shines on the resistor, the electrons in the atoms, they start to move around more, so more current flows, okay? So if you've got more current flowing, obviously that means there's less resistance, because more current is flowing. So yeah, they get energy from the sun, move around more current flows. So one of the things, they'll tell you is, on BBC Bite Size, without really explaining it, is that these things are very useful for security lights. And I just accepted that for ages, until really quite embarrassingly recently, I was like, wait, what? How does that work? Because you're like, oh yeah, LDR, you know, they change when light shines on them, so it makes sense. Security lights. No, though, no. Are you seeing what I'm seeing? Let's say we've got a power supply here, attached to a bulb, a filament bulb, and let's say I put LDR in this circuit, okay? Put it over here with the lights. So it is dark. It's dark. So the atoms in the LDR don't have that much energy, so the resistance is high, okay? The electrons are more kind of bonded to their atoms. So it's dark, not as many electrons free, resistance is high, so the resistance in this circuit is high, so the current is low, so the bulb is not lit up when it's dark. And then it gets light shines on this thing, electrons move around more current flows, the bulb turns on in the light. Like, it took me an embarrassingly long time to work out the answers to this problem. I'm like, how is this thing good for security lights? It's the opposite of good. And then I was like, putting it in the circuit wrong. Can you see how you would put that in the circuit to get a useful security light? This is a massively oversimplification, but very sort of, to simplify a bit. Look, if you put it in parallel, now what happens? So it's light. So the resistance of this thing is really low because, electrons, like energy. So the resistance is low. So the current always chooses the path of least resistance. So current going along here, if the resistance of this thing is low, the current is going to choose to go through here. It's going to avoid the bulb in the light. And then it gets dark. And the resistance of this thing massively increases. It's dark. So the current now chooses the path of least resistance, which is through the bulb, and the bulb comes on. That's nice. It's not that complicated, but it's just really pleased me that I know that now. I was finding that very irritating. Okay, let's move on. So that's LDRs, light-dependent resistors. Let's cover thermistors. I'm going to flip the question around now. I will tell you that a thermistor, as it heats up, its resistance decreases. So similar sort of thing, yeah? A thermistor, its atoms gain energy, electrons gain energy, and more current, so less resistance. So can you draw me a graph, please, of what a thermistor looks like, just to give it a quick sketch? You've got resistance on the y-axis and temperature on the x-axis. Draw me a graph of how a thermistor behaves. As it heats up, as temperature increases, its resistance decreases. And if you finish that, and you're like, oh, obvious, think about how you're going to remember that this is the circuit symbol for a thermistor. It's like a boring old rectangular resistor, but with a stick person's golf club whacking into it, or a stick person's foot or something. Don't know. How are you going to remember that that is the symbol for a thermistor? Let's have a look at this graph. What was I looking for? Well, I was looking for a downwards slope. So resistance starts high when the temperature is like 0 or whatever. And then as the temperature increases, the resistance gets lower. Did you remember to not have it touch 0? Well done if you remembered that it's very unlikely that you're going to get 0 resistance. Here is a picture of a thermistor. Aren't they pretty? They sort of look like little peas. So if we were in a classroom, these metal bits coming off them are like the wires, yeah? So I would put this in a series circuit. I would dip the tip in some warm water, say, and we would have a look on an ammeter and a voltmeter to see what happened as it warmed up. You'd put them in like different temperatured water or something, but I'm sorry, you're just going to have to imagine that. And let's all move on with our lives. So yeah, that's a thermistor. They're useful for all kinds of things. But basically any time you can picture electricity and heat being together. So like probably I've got a really annoying beepy sound that comes on in my fridge when my fridge thinks the door's been open too long. That'll have a thermistor in there, a circuit that can kind of detect temperature and make an alarm go off. Okay, it's the moment you've all been waiting for. It's time for circuit symbol bingo. This was really doing people's heads in on Facebook. Well, it wasn't. They were being very enthusiastic, but they were all getting bingos too early. So how it works is, if you've been on my Facebook group and you've downloaded the worksheet, you've probably got this in front of you. I'm going to show you some circuit symbols. I'm going to give you some questions, and what I want you to do is just to like cross them off, or if you're just using the screen, then just have a look at it and note down where they are. And then we're not going to do diagonally, but when you get a row of 4 or 3, like horizontally or vertically, then you say bingo. That's it. It sounds fun, doesn't it? They were having a nightmare yesterday. But we'll give it a go. I'm going to, like I say, ask you questions about them. Here we are. So yeah, you can't go diagonally, and it's 4 in a row or 3 in a row, that is a bingo. Okay? I mean, I don't know. I'm a bit paranoid now because everyone started shouting bingo far too early, and it was very, very concerning. We'll see how we get on. Number 1. This thing gives off light, and you've got to be careful which way round you put it in the circuit. Which one is the symbol for something that gives off light, and you've got to be careful which way round you put it in the circuit. That's number 1. Number 2, you can't vary the resistance of this resistor. Number 2, you can't vary the resistance of this resistor. Which one is that? I'll get a bit more straight on for you. Number 3, this measures the amount of energy per charge across a component. That's number 3, it measures the amount of energy per charge across a component. Number 4, it's a symbol for a power supply. That's number 4, it's a symbol for a power supply. So number 1, it gives off light, you've got to be careful which way around you put it in the circuit. Number 2, you can't vary the resistance of this resistor. Number 3, it measures the amount of energy per charge across a component. And number 4, symbol for a power supply. Number 5 is the variable resistor. Which one is the variable resistor? So I don't know why I said that in such a spooky voice. Number 5 is the variable resistor. Number 6, it's something that its resistance decreases as it heats up. You've learned so many of these so fast, I'm sorry. This is hard. Which one of these does the resistance decrease as it heats up? So number 4 is the symbol for a power supply. Number 5 is the variable resistor. Number 6, its resistance decreases as it heats up. Number 7, quite pleased with this one. For number 7, its resistance increases as it heats up. Which one of these circuit symbols is something that when it heats up, its resistance increases quite noticeably? And number 8, resistance decreases when light shines on it. Number 8, resistance decreases, more current flows, when light shines on it. Are you all shouting, bingo, Laura, bingo? Which line is it? Can you see which line it is? Have you not been shouting bingo, but have you been shouting bingo for 12 minutes? Let's go through the answers, see what you think. It gives off light, and you've got to be careful which way round you put it in the circuit. That's this LED, this light emitting diode. See the light coming off. Number 2, you can't vary the resistance of this resistor. That was just a boring old rectangular resistor, the fixed resistor. Number 3, measures the amount of energy per charge, the amount of pizzas per bike. That's the voltmeter. Well done if you got that. Ammeter is, what's that amount of charge per second? Bikes passing a certain point per second. 4, the symbol for a power supply. So that was number 4. So just the 2 dots with a gap in the middle. Number 5, the variable resistor is this one. The variable resistor is being shot through the heart. Number 6, resistance decreases as it heats up. That is our new thermistor, which is the golf club beating up a fixed resistor. I don't know. Number 7, resistance increases as it heats up. I was thinking that was the lamp. Number 7, the resistance increases as it heats up. Yeah, that's why we get it's not directly proportional, the current and the voltage to the graph. And resistance decreases when light shines on it. And hopefully that was quite easy because this thing's the only thing with light shining onto it. And it's a resistor. So that is the light-dependent resistor. Which was number 8. So the bingo that I think that you should have is this one here. Well done if you got this line. Well done if you got any old line, but you're still here. And now you know. Okay, so that's the end of the lesson. Well done, you lot, and thank you for coming, as always. Much appreciated. I'm having a lot of fun with these. I'm going to go over to my Facebook page and just see if anyone has said hello. Because whenever I'm live, I always put a post on Facebook saying, if you want to say hi, please do. If you want to support me, if you usually pay for your lessons and you are enjoying these, if you are using me as a resource, you totally can. Everything that I do is free. This is my business model. Oh, it's snowing. It just started snowing. Oh, sorry, distraction. yeah, if you want to support me, you can. Everything's free. There are, in my Facebook group, it's well worth finding this PDF of homeworks and further reading. It's up there now. If you're watching this live, you can go there now and get it. Just all the past paper questions that I found that I think you should be able to answer after this lesson, and some useful websites that I think summarise really nicely what I think I've taught you today, but you can check that for yourself. Yeah, if you want to pay me for all those efforts, then you can. I'll send you some rainbow glasses, and I'll send you the Science magazine. Excuse me. If you sign up now, you'll get the PASS magazine, a PASS magazine when you sign up, and then you'll get the next issue, which is on sleep, which is at the printers now, so you should get it within a couple of weeks. So a very good time to sign up. Thank you to everyone who's supporting me. Okay, I'm going to read some comments, and then I'm going to look at the snow. Comments, is this Chloe? Oh, it is Chloe! Should I be worried about my brain melting? Hello, Chloe. I don't think so. You're writing this. This is a good sign. Hey, Juaria and Ryder. Hello. Hello. Good to see you guys. Right. Okay. I'm going to go and advertise tomorrow's Lego Storytime show, which is on snow. 'Cause it's snowing. Okay. See you soon, everyone. Have a nice